Hi, everybody. Thank you for joining us. I'm Dan. I'm the community manager at Speedb, and we're here with Peter Dillinger, Peter Dillinger, and Guy Muir, the CTO of Speedb. Peter is from the RocksDB team at Meta, and he's here to talk with us about or do a drill down into HyperClockCache.
All right, thanks, Dan. Thanks for coming. Thanks for inviting me. Appreciate all the work you guys are doing to help build and develop the RocksDB community. I'll quickly acknowledge, the colleagues listed down at the bottom who helped with this work tremendously. Let's jump into it. RocksDB HyperClockCache drill down, scalability, efficiency, and usability, because all of those matter. Okay, so let's talk about some history of RocksDB efficiency and parallel scalability in particular. So, as many of you probably know, the traditional approach to parallelization is you use a mutex, and when you have multiple threads competing for something, then they, when they have to access a shared thing, they acquire a mutex, and but that can lead to contention where one thread is waiting on the other, and that gets worse and worse as you have more CPU cores and more parallelism, and in the systems we see today, they can have dozens, sometimes hundreds of threads, sometimes all running at the same time. And so we don't want, in many cases, we have to get away from the model of using mutexes. And RocksDB is, part of its success, I think, has been taking some key components and implementing advanced parallelism that does not rely on mutexes. So, for example, on the write path, back in 2015, we implemented write thread grouping in a lock-free manner. Also in 2015, we added the skip list, which is a lock-free mem table. In 2014, a little earlier, we did the thread local version of a structure called the super version, which is critical to the read path of RocksDB, making sure that if you have a bunch of reads going on, that they're not all trying to figure out what the latest version of the database is. But something that's been kind of sticking around and popping up its head as bothersome from a performance and scalability standpoint is the block cache. And our standard implementation for that has been the LRU cache. LRU stands for least recently used, and that's named that way because of the eviction policy. And this is not a disaster. It scales pretty well because of some sharding that we'll talk about in a minute. But it's still mutex based, and so there can still be sources of contention, and that can be a performance bottleneck in some cases. And I thought I'd just point out that there's also something called the DB mutex that controls certain operations, but for the most part, that's contention on that is not high for a lot of applications. And so it wasn't the highest priority to tackle at this time. We try to keep DB mutex contention pretty low and have been reasonably successful at that. So we're going to focus on this block cache case that's been proving troublesome for some scalability. Okay, so let's talk more about what we mean by the RocksDB block cache. So the user calls dbget, and this is kind of the normal function to get me the value of this key in the database. it will look up some metadata. I'm skipping the memtable pass here. It'll look up, it'll actually use the super version to say, hey, what does the LSM look like? And so what files do I potentially need to look in to get data for this key? And it might say, oh, I potentially need to look in these files for the data associated with this key. And for each one of those, so here I'm going to assume that we're using an option called cache index and filter blocks, which means every time so a typical access to an SST file will start with a filter check to try to quickly determine whether the key is in that file or not. And if the filter check says, hey, that key might be in this file, then it proceeds with looking in the index block to figure out which data block it needs. Or if the filter says, no, that key is definitely not in this file, then it can just go on to the next file. And so when you're using this option, which is, it's a pretty standard option to use for large scale databases, at least at Meta. I think it's kind of a risk mitigation thing. If you don't use this option, then you're always keeping filter and index blocks in memory, regardless of the size of the DB, and that could risk, running out of memory and the kernel killing your process because you ran out of memory. And there are some, I'm sure Guy is wanting to point out some alternatives that they've recently come up with to try and do something in the middle, some better things in the middle, called smart pinning or something. Is that?
Yeah.
Is that
So if you serve me that ball, then I'll take it happily. So as you said, if you use that, that means that everything is pinned, and it will be pinned until the file is closed, and you get into a risk to get either out of memory till kernel kills you. That's a big deal, but you might get it just above the memory you plan to. In the latest version of Speedb, version 2.6, we've introduced something that is called static pinning, which means that we will pin everything, but we'll stop pinning for you when you reach a threshold. So we will make sure that you will enjoy the benefits of the pin as Peter described them, as long as you have enough memory. And once you don't have enough memory, we will automatically for you stop pinning and move back to the LRU. So thank you for that, Peter, and take it back.
Yeah. We like to have lots of options available because one size does not fit all. So we're gonna continue thinking about like the cases where you're using this option, and that means that the block cache is getting a lot of lookups because for each level of the LSM that you're accessing, you're doing at least a filter block lookup in the block cache, and potentially an index block and a data block also. Historically, one of the funny things about accessing so many filter blocks is actually looking up the filter block in the block cache. In a lot of cases, is more expensive than checking the filter, checking whether the key is in the filter, which feels kind of backwards, but and hopefully this work is addressing that. So anyway, sometimes people wonder why the block cache even exists, and I want to touch on that very briefly. The OS it has a great mechanisms for caching data that's on disk, often called the page cache. The thing that there are two key things that the page cache does not provide us that we need with the block cache. Arguably more, but two in particular. The first is that the data on disk for almost all of our use cases is going to be compressed using something like Z standard, or we also like what's the other one? LZ4. to use the data in memory, we need to uncompress it first. And so when we load stuff into block cache, we're uncompressing it. And the second big reason is the data, we add checksums to the data on disk, and we need to check those checksums before the data. Storage layers are just not reliable enough for us to rely on them without checksumming. Yeah, and so that's why we have our own block cache, aside from the OS page cache. And you can end up with a situation where if you're using traditional POSIX IO, where you're sort of double caching things, like in a compressed form in the page cache and then uncompressed in the block cache. And if you use our direct IO options, you can avoid that double caching. And a lot of our internal use cases use direct IO. Okay, so let's look a little more deeply at LRU cache and some of the potential places for improvement. So fundamentally, LRU cache is a hash table. We have a way of identifying keys, which are logical blocks within SST files, and assigning those cache keys, which is different from like your DB key. And so fundamentally, it's a hash table. I mentioned earlier that we shard the mutexes, and what that means is we, based on the hash value of that cache key, we choose we have multiple hash tables, and in a typical configuration, there would be like 64 shards. So we would, the hash of the key would essentially at random choose one of those shards, which is responsible for storing that cache value if it exists in the cache. And so that's this layer here. Then we have like a raw hash table, which in LRU cache, it uses chaining. And we have these things called handles, which help to manage the lifetime of objects and allow you to, for example, like iterators need to hold on to blocks potentially indefinitely. And the handle keeps track of the reference count of these entries in the block cache so that they can stick around potentially indefinitely, or make sure that they're reclaimed on an LRU basis, et cetera, et cetera. And one of the interesting things about this hash table, if you look at a lot of hash table implementations, they're heavily optimized for making sure that they can have a high load factor without falling down in performance. But in the block cache, 98+% of the space usage is in like the values that we're referring to. And so having a little extra space in the table itself, having a medium to low load factor is not a big deal. It's not wasting much space compared to other hash table use cases. So this is one of the reasons sort of out of the box hash tables don't always work great with the block cache because there's some sort of different trade-offs than usual usual hash tables. So we also have to talk about, all right, this is a very highly concurrent object. So like in the setup I talked about, each dbget is going to be doing multiple lookups on this hash table. And so it needs to handle concurrency. And basically everything to the right of the handle is immutable. So we don't really need synchronization on that. The handles keep a reference count, as I alluded to earlier. for the purposes of tracking for entries that should be evicted. And basically everything between the shard and the handle in LRU cache, this is mutex controlled. It, when you start to do a lookup and you figure out which shard this entry belongs to, at that point you have to lock the mutex even before you like index into the hash table, because the LRU cache, as it's like a normal hash table in the sense that once it gets too full, it will double in size to make room for more entries without the performance falling apart. But this means that one of your operations is going to lock the mutex, and then it's going to double the size of the table, iterate over all the entries while holding the mutex. I think in practice this is not a big deal, but it does probably cause some slight hiccups as your DB is getting started. But the big deal about that is that you can't, you have to lock this mutex before you even follow the pointer to the table. So you really have to hold that mutex for a lot of pointer chasing. Like you have to follow the pointer into the table and then to a handle and potentially another handle that it's pointing to, etc. So it's not ideal. So one of the things you might say is, okay, so what about if we used a read-write mutex? Because a lot of times we're just trying to look up things in the block cache and not necessarily insert new things or erase things. But the problem with that is in an LRU cache. So when you're using LRU, especially, every read is a write. So essentially every read is a write, because when you read an entry, or especially for us when you're done reading an entry, you have to add that entry to the LRU list. So someone who thinks that they're just reading from the LRU cache is really modifying the state of the cache, because it's updating that information about how recently it was used. Yeah, so we can't just use a read-write shared mutex. We have to just use an exclusive mutex. There's some other things that we could consider to building better solutions to this. One is RCU, read copy update, or something related called hazard pointers. And these are really powerful tools, but we decided to kind of go lower level than that in trying to optimize this as much as we could optimize it. We kind of went on an exercise of like, how can we strip this down, make it as streamlined, fast as possible? What do we end up with, and how can we make that useful? So I'm not going to go into the details of this, like RCU and can we even like get rid of the handles? That's another difficult question that would take forever to try to explain. So anyway, let's move on to kind of a high-level overview of like what the state of the world. So I'll try to give you some facts before we drill into more interesting details. So last year we developed this LRU cache alternative, HyperClockCache. Recently we've sort of internally that implementation is now called fixed HyperClockCache, because it used a fixed size table at creation time. The size of the table is fixed, and now coming up in the next release, we have a newer version of HyperClockCache that shares a lot of code, but also has a substantial amount of different structure to it, so that the table can grow automatically. And that required some kind of clever and hair-pulling engineering to get that to work. And internally we're calling that auto HyperClockCache, but from a high level, they're similar enough that we just, in the public API, we call them both HyperClockCache. And so, like, what at a high level, what's offered by these two implementations? Why should you care? So we can go through that briefly. So one of the first things you talk about with a cache is what eviction algorithm is it using? We talked about LRU with LRU cache, and it's worth pointing out that our LRU cache has something called midpoint insertion that is supposed to prevent things like range scans from evicting higher priority blocks. So ours is not a pure LRU. It's also sharded, which makes it slightly impure, but in practice, it's pretty close to LRU. And the midpoint insertion helps to prevent some of the LRU worst cases. But yeah. So our HyperClockCache, both revisions use the same kind of eviction logic. The advantage of clock from a parallelizability standpoint is the eviction metadata is very local to each entry in the cache. When you say that when you use an element and you're done using that element, in a traditional clock setup, you would just set a bit saying, hey, this value was recently used. And some other process would come through and occasionally clear those bits. And then if on the next sweep it sees that this value was not used, then it would be evicted. There's a generalization of that called a counting clock that is a little bit closer to LRU. It's a little bit more precise, slightly better approximation of LRU. And that's what we're using in HyperClockCache. And it's worth noting that we're using fewer shards, but we are still using sharding to reduce some of the data contention, even though it's not like blocking contention. And it's worth noting that the LRU cache does have some uses that HyperClockCache doesn't currently support. So you may have heard of row cache, and internally we have something called table cache. And these are only work with LRU cache, and we might fix that someday, but it's not a big deal overall. So I mentioned earlier this problem of what I call indefinite pinning, where like iterators need to hold on to something in the cache and keep it there potentially indefinitely. And this is one of the challenging things for this hash table design-wise. A lot of kind of off-the-shelf hash table designs, concurrent hash table designs, rely on being able to like move things around, and we can't really do that when we have to support this indefinite pinning, at least with handles. So anyway, automatic table sizing, that is, the hash table part of it grows as needed. Yeah, we discussed how LRU cache does that. Potentially an annoying part is like the high latency where it holds the mutex while like doubling the size of the table. The old HyperClockCache it worked by you had to provide a hint that would allow it to guess an appropriate size for the table. And that works most of the time, but it doesn't, it can have trouble when you use things like Buffer Manager, where it's hard to predict exactly how many entries are going to be in your block cache. So this is what the thing that we wanted to fix with the automatic HyperClockCache was to allow it to automatically size the table for efficient lookups. And we've successfully done that. And in fact, it's like low latency. It can kind of grow 1 or 2 elements at a time as needed. So let's talk about some of the concurrency, some more specifics about concurrency. So the LRU cache, as we said, relies on a lock or mutex lock on the shard. For lookups, both of our HyperClock caches are fully wait-free. I like to use the word wait-free rather than lock-free. Lock-free can kind of mean some different things, but wait-free means that no thread is ever waiting on some other thread in order to make progress. So when you're doing a lookup in HyperClockCache, your current thread can always make progress toward finishing that lookup without ever waiting on another thread. There are some cases in the automatic version where a concurrent modification can cause you to like retry something, like a small block, kind of like a compare and set has to retry. But eventually you're going to, and this is like at the entry level. So if somebody else modifies this entry, then I might have to like retry some instruction to make progress. But eventually you're going to make progress. So insertion is also fully wait-free in the existing version. There are some kind of corner cases where it's not wait-free in the newer automatic HyperClockCache, but it's like I have internally, I have a counter for how many times a thread has to wait on another one. And sometimes when I run a benchmark that's just like hammering the cache, it'll end up with no cases of one thread waiting on another, just because like the structure of how what has to wait on what, it's kind of ordered in a way where it doesn't usually happen. So one of the ways that we make this work is that we relax some of the guarantees that the cache provides. In particular, like if 2 threads happen to be trying to insert the same value at the same time, which would be kind of rare and weird. HyperClockCache doesn't guarantee that only one of them survives. So you could transiently have 2 copies of something in the cache, but this is not a big deal. You know, only one of them is going to end up as visible, and the one that's sort of shadowed by the other one will end up just kind of dying of old age and being evicted. But we do have, you know, we do have guarantees like if you insert something and you do a lookup that, you know, you can show happens after that insertion. If that insertion has not been evicted or erased, you know, we guarantee that you're going to see that. So we're not playing any games with the availability of entries in the cache. So that's good. Yeah.
You know, maybe it's worth linger a bit about how about the eviction policy, about the clock eviction policy.
Okay. Yeah. Yeah. I think I touched on that a little bit later, but yeah, we can chat about that a little bit. So a counting clock, and we implement sort of a bounded counting clock, where we can. Right now it's hard coded, but we might make it configurable in the future, where you can count as high as 3, and then the count increases every time the value is used, and then decreased every time the sweep of the clock pointer passes by it, and it gets evicted when it's when that pass finds that it's 0 and tries to decrement it one more time. This is an approximation of both LRU and of most frequently used MFU, because the counting aspect means that if you have several accesses, it gets promoted. It will stick around longer than it would if you just had one access at that same time.
Mm-hmm.
So potentially this could be better in some cases. We haven't really seen that. We haven't really noticed a consistent difference in the hit rates between the LRU algorithm and the clock algorithm. Yeah. Does that answer your question?
Yeah.
Okay.
And you're saying you might open up the number 3 as an option, just to give them more chances to stick in the cache if they were once used many times. Actually, the 3 makes sense, honestly.
Yeah. 3 is kind of makes it like within some factor of LRU order. Okay. Yeah. And I think I'll touch more on these bottom 2 points in one of my later slides. So let's try to breeze through some of the low-level details. So just to show you some of the cool technology that underpins this. So part of the part of the HyperClockCache that is shared between the 2 versions, I call it the low-level protocol, and it has to do with how we manage each slot in the cache. So you could imagine, like, in a silly universe, we had a cache with just one slot available. This is the protocol that would be used to handle that one slot. And first of all, with the HyperClockCache, we pre-allocate and recycle these handle objects. So there's no synchronization needed to follow a pointer to the handle. So if we have a pointer to a handle, like you would have to refer to a cache entry, there's no synchronization needed to follow that pointer, because that pointer is going to survive the lifetime of the cache. We'll talk a little bit in a few minutes about how we do that with the automatic table sizing. We do some magic there. So one of the key parts of this in the low-level protocol is we have this 164-bit atomic value that holds kind of all the important mutable state about this object, including, like, what what state it's in. Like, it could be empty, or it could be exclusively locked, like while it's being populated or while it's being freed. Or it could be in a shared state where, like, people are allowed to reference it or unreference it. And so this atomic meta also includes other information. So we can kind of update multiple things with just one atomic operation. The cache key, another important bit is the cache key. The LRU cache supported historically we needed variable size cache keys to identify blocks within files, but we have a new, well, it's probably a couple of years old now, a kind of a clever system to identify these in a stable way using fixed size identifiers. And it's kind of like universally unique identifiers, but with some different, interesting, fun differences. You can look at this paper that I reference here if you're interested in the interesting, fun differences. So if we drill into that atomic metadata a little bit more, so logically speaking, there's a reference count and then there's eviction data. And, you know, you might think of these as logically different things, but they are, at least in the clock universe, they're very related, because when you're updating the reference count, you're often going to be updating the eviction data because you just used the value. So the clever thing that we do with this is, instead of having an explicit reference count and an explicit clock count, instead we have an acquire count and a release count. And so we can compute from these the reference count and the eviction count down. So the reference count is the number of acquires minus the number of releases. So, you know, that makes sense. I increment the acquire count whenever I newly reference this, and I increment the release count when I release a reference to it. And the eviction countdown only makes sense when there are no references to the entry. So when the acquire count is equal to the release count, and in that case, take either of those values, and it's the minimum of that value, or 3. And the reason we do it this way is that we can have super fast logic for updating this information on lookup and release. So
Why not just use 1 and just increase it and decrease it as you reference it or as you pass it by?
Well, that would just give us a ref count, but that ref count doesn't tell us, that doesn't give us a clock count. So we would have to update both a reference count and a clock count. In some cases, maybe you could make that work, but I think there, you know, if you drill into the details of exactly what operations go on, I think this is more efficient. Yeah.
Okay, fair.
Yes, there was a session of, you know, me trying to figure out, you know, how to minimize the number of atomic operations for all the common operations. Like, I just looked up something and I'm now releasing it. You know, these are the really hot path operations. So yeah, for those, we just do a simple increment of the acquire count or a simple increment of the release count. And one of the cool features that we might use in the future is, or actually we also use it internally, because sometimes we have to reference something inside the cache to figure out, like, okay, does the cache key actually match? And for that, we will increment the acquire count to keep the entry from being like evicted in parallel. And then we need to release the entry, but we need to pretend that we never acquired it, because we don't want to update. We don't want to make it look like we actually used it from a user standpoint, just for internal purposes. And so in that case, we just decrement the acquire count to say, oh, nothing to see here. I didn't touch it. It was not actually used for anything useful. Yeah. So yeah. Oh, another fun thing is that we can we can kind of do lookup optimistically, where if we say, oh, I'm going to look in this handle for a certain key, I don't even have to look at the state of the handle. I can just increment the acquire count, and if that handle is empty or exclusively locked by somebody according to the state part of the atomic, that incrementing the acquire count just has no effect. It doesn't mean anything. And so I don't have to like check and see, oh, is it safe for me to increment the acquire count? And to do that safely, you would actually have to do a compare and set to make sure that nobody concurrently updates something. So this is really just allows you to do kind of a blind update of these, even if the handle is in the wrong, quote unquote, wrong state. So that's part of the magic that's been in the HyperClockCache for since the one that was released late last year. So let's talk about the high-level protocol, as I call it, that sits on top of that. That basically we have to organize a set of handles into a hash table, and we want to minimize additional synchronization overhead. We want to minimize like indirections, so like pointer chasing, and we want to minimize the number of CPU cache lines that we're hitting. And we want low metadata space usage, etc. And so here's how the current, fixed HCC works. We have a flat array of handles, one for each 64-byte cache line. The size is determined at creation time, and it's determined by the user providing an estimated average uncompressed block size. So typically, if you pass in the same setting that you use for the block-based table options block size, typically that would work. But it's not easy for us to just like take that option and use it ourselves, because the cache is created before these other options. And also you might have multiple column families sharing a cache and they have different block sizes. So we kind of have to leave it up to the user to, in this version, we had to leave it up to the user to tell us what size to use, because there wasn't really a practical way for us to figure it out ourselves. And once you create that array of handles, like there could be threads accessing it and you can't really move it in order to like create a bigger one or something. So this version uses open addressing and double hashing, kind of like a lot of hash tables, but no relocation is allowed in order to handle those sort of indefinite pinning use cases, where some iterator has a pointer to the handle, that iterator could stick around forever. In order to handle this, we have a displacement count on each handle, which tells us how many times something was added further down the list of probing locations. It's not too important that you totally understand that. By the way, this is sort of like a Folly, a hash table in the Folly library called F14. If you ever need a really fast hash table, this is what we use in Meta. And there have been some pretty big efficiency gains, but with this, I recommend you check it out if you want a faster hash table for a lot of different applications. It doesn't natively support concurrency, so it's not like a plug-in thing that we could use instead of LRU cache. But we've borrowed some ideas from it. So because we have this kind of flat array of handles and we can always follow a handle pointer, we haven't introduced any additional synchronization overhead. It's always safe to check a handle and see, hey, is this the one I'm looking for? we've just added these displacement values, which allow us to determine, okay, I've probed far enough. If I was going to find the entry, I would have found it by now, and so I can stop probing. Yeah. So let's talk about the new version that should be coming in the next release. That'll be cut at the end of this week and probably released to the public sometime next month. Oh yeah, coming in 8.7. Yeah. So I've been talking about many times how how we take advantage of the fact that we pre-allocate all the handles, and that allows us to follow these pointers to handles without worrying about concurrent modifications. So how do you do that if you want to have the structure grow dynamically? And the way we do that is with an anonymous mmap. And basically this allows us to reserve virtual address space. And so we can make that virtual address space reservation kind of as big as we could foresee needing it to be for kind of impossibly small block size. But the way the operating system handles this is that it only allocates physical memory as you actually use it. And so as long as we only use like some prefix of that space, it's only going to occupy that many pages of resident memory. And so we just need to come up with some clever hash table scheme that allows us to grow the size of the hash table, to occupy more and more space, growing, in one direction through virtual memory, which gets mapped to resident physical memory. So there is a very standard solution for this, although working out a lot of details to work out, and that's called linear hashing. And basically you're stripping off some number of hash bits for the location, and there's some threshold between, for some values you're going to strip off like 4 bits, and for some values you're going to strip off 5 bits, and to grow the table you kind of bump up that threshold for when you use n bits, when you use n plus 1 bits, and then eventually you're using n plus 1 and n plus 2. But it's nice low latency, because you're basically, to grow the table by 1 entry, you're taking an existing chain, or as I call it, and splitting that chain into 2 new chains. So in this one, we're using chaining, which is essentially, like a linked list of entries in the table, because otherwise it doesn't seem like there's a practical way to, we're not allowed to move entries that are already there. And so how can we organize those? If they were added when the table was really small, how can we keep those organized into a big table if they're still there when the table is much, much bigger later? And so we basically have to assume some cost of, like, okay, we're going to be doing some pointer chasing, but there's kind of a clever way we can, in many cases, avoid a lot of the cost of that pointer chasing. And one of the things we do is, you need like head pointers for each chain, and we basically interleave those head pointers with the entries themselves. So part of each handle will be a head pointer and a next pointer. We're forming a linked list here. And in the common case, we will try to, when we're trying to insert an entry, we will try to insert that entry in the same cache line as the head pointer. And we can, if in stable operation, once the cache is up to its full size, a pretty large proportion of the entries will be sort of at home. The entry is in the same cache line as its head pointer. So we have a really cheap lookup path in a lot of cases. Yeah, so that's one of the clever bits. A lot of details that we don't have time to go into. But we have almost zero additional synchronization overhead, especially on the lookup side. We do have to do some sort of careful stuff on the lookup side where, as we're iterating over the linked list, we could fall off. I like to call it falling off our chain or losing our chain as we're doing a lookup. And so there's some things we do to make sure that we always see the whole chain. And we might have to retry a few things if there's a concurrent modification. But still, lookup is kept fully weight-free. And most insertions are weight-free also, especially if an insert doesn't have to evict anything. That's also fully weight-free. Anyway, I'm not going to spend a lot of time on benchmarks. Your mileage will vary depending on your workload and your hardware and some stuff like that. But I think the high level takeaway is that we were trying to solve the kind of hot read scalability problem. Where if you have a database that has a high level of reads workload with a lot of threads, on hardware with a lot of cores, we wanted to make sure that ran at full speed. And in a sense, we're trying to solve the kind of stressful case. How does the DB behave when it's under stress? You might have a spike in reads. Yes, we care about average cache efficiency, but a lot of times, resources are allocated for the kind of the worst case, the P99.99 case. And so when you're, under a spike of reads, how does the system behave? And, Mark Callahan did a nice blog post showing, oh yeah, if you've got a lot of parallel reads, then the HyperClockCache holds up a lot better. As you scale the number of threads that are hammering the database. This data comes from the old one, the fixed HyperClockCache. The auto HyperClockCache has very similar performance. It might be slightly slower in some cases, but the scalability is very, very similar. So I don't think we need to dwell on that too much. It's not all for free, like the automatically sized table, but it was close enough. I initially wasn't sure if this version of it would need like a different name, because if it was, if its performance characteristics were sufficiently different, then I wouldn't want to call it HyperClockCache. But the performance was sufficiently close that I was like, oh, this is not that different. If you really, really care, you might see some difference and want to tune that, but essentially it has all the same benefits. So let's talk about, try to summarize, where the benefits are, and what potential complications you might have. how things will go bad. LRU versus HyperClockCache. So one of the things that I didn't mention about LRU and the sharding mutexes, locking the mutex for each cache shard. Suppose you have one hot block that you're reading a lot in your LSM, and this could be like you have perhaps you have a small flush where you have a small file and it's getting hit a lot, an L1 file, and it's getting hit a lot. If you have a single hot block, you suffer this mutex contention in LRU cache, regardless of the number of cache shards. You could have lots of threads hammering, looking for the same entry, and in that case, sharding doesn't matter because they're all looking for the same block, and they have to wait in line for the mutex in order to even read that block. And both versions of HyperClockCache completely solve this problem. It's they're just doing atomic operations. Yes, they have to load the cache line between the different cores, but like that's super duper fast compared to acquiring a mutex. And obviously, as we alluded to earlier, if you have not enough cache shards to handle the amount of parallelism you're seeing, you're obviously going to see mutex contention. Another problem that comes up with LRU cache is if your cache is too small or you have too many cache shards. So choosing the number of cache shards can be like a tricky game if you have a small cache. If you have a large cache, it's pretty safe to have a lot of cache shards. But if you have a smaller cache and too many cache shards, you could end up thrashing that shard because it's not big enough to hold all the hot data that needs to be in that cache. And there could be kind of like random skew between the shards where one of those shards is just thrashing because it's got too much stuff assigned to it. And this is a problem that shows up. And HyperClockCache, we kept the sharding in it because there is some benefit to having stuff like, what's the current usage in this cache? Sharding that sorts of data does provide some performance improvement in the HyperClockCache, but the diminishing return of more shards is much sooner for HyperClockCache. So we've tuned it to have much fewer shards, and so this problem is much less likely with HyperClockCache because we can get away with a smaller number of shards, larger shards, where you're unlikely to have this thrashing problem. In theory, you could have cases like, I guess I should also point out this one, which is kind of related. You could end up, the case that you would want to worry about with HyperClockCache, if you have a small cache. If you have a large cache, you basically don't have to worry about that. Like if your cache is in the gigabytes, you basically don't have to worry about this. If you have too much penned, then you could, the way the clock eviction works is it has to go searching for things that are evictable. And if you have too many entries that are pinned, then that process becomes less and less efficient. And so you could end up just kind of like burning through CPU looking for things to evict. Whereas the LRU cache keeps a list of things that are evictable, and it can decide instantly, is there something evictable? And if there is, I know what it is, and I can just evict it. Basically, this is not a problem in large caches because you're never going to have all that stuff pinned, and you can find things to evict. But it is a potential concern for small caches. If you use a lot of iterators or something or smart pinning or something that would have a lot of stuff pinned. For the eviction algorithms, I could see things going awry in either case. You know, sometimes LRU is like the thing you want to use. Sometimes, but it's also possible that LRU could fall over in some kind of like scanning cases. And in that case, you know, you could see a win either way. It's hard to predict which is going to be better. We have seen some evidence that HyperClockCache puts more stress on the memory allocator. We haven't fully gotten to the bottom of this. For the most part, it should not be a concern, and it might be only related to certain versions of JE-malloc. And that could lead to the memory. Yeah, the way I put this is like HyperClockCache is too fast for the memory allocator to keep up. It's just too awesome.
It's a good problem to have.
Yeah.
While we're on this slide, can you, like, very high levelly describe a use case that would be better for LRU versus HyperClockCache? So which use cases would you choose this, and which use cases would you choose that?
Yeah, I think so. If you have a lot of read, if you have read heavy traffic, and you have a large cache, I think that you're going to see a lot of benefit with HyperClockCache with almost no concerns about trouble. The auto HyperClockCache is currently experimental status, so we haven't fully validated it. And in fact, Mark Callahan helped me find. He noticed a performance problem in some cases, and I'm working on fixing that before the release is done. So don't use the auto HyperClockCache right away in production, but I expect it'll be marked production ready in a couple of 2 or 3 months or something. But if you're willing to provide that hint on the block size, the fixed HyperClockCache provides a lot of benefit for those read heavy workloads.
In what scenario would I choose the LRU?
Yeah, the LRU is kind of in some ways a safer choice for workloads that aren't read heavy, but if you're more concerned about, like, oh, what if my hit rate goes up by like 1%? Would that be a disaster for my IO performance? LRU might be a safer choice for the moment. But maybe you would find that on your workload, the clock eviction gives you a better hit rate. I don't know. Yeah, so I think it's also tricky with smaller caches because you can definitely hit this, especially if you're using full filters, not partition filters. You can hit this thrashing problem with LRU cache, and it's really bad, and it can just kind of pop up randomly because it's like a random. There's the cache shards are assigned essentially randomly, so it can kind of pop up randomly. So you have to consider that versus, like, if you ended up in a situation with HyperClockCache in a small cache, if you ended up in a situation where you had a lot of stuff pinned, maybe you were not collecting reclaiming iterators fast enough or something, you could end up with a situation where your eviction is using a lot of CPU.
Okay, fair enough. We are a bit over time already.
Yeah.
I know you have a few more slides. Is there something you want to run through them quickly? We want to leave some time for questions.
Yeah, maybe I can do this slide in 30 seconds and then we'll be done. Yeah, so The way I see the HyperClockCache long-term value proposition is that the RocksDB block cache is kind of like a meritocracy for RAM. Like it allows different things to compete for RAM, like filters and to some degree, hopefully someday, like mem tables and data blocks, and it allows, the system is more efficient if we allow things to compete for RAM. And HyperClockCache lowers the CPU overhead barriers to entry to like allowing things to participate in this meritocracy, like index and filter blocks. If you're not pinning them, they can kind of compete on their own merits for RAM. And this could be useful for next generation filters related to, there's a paper called Elastic BF that goes into this. And the auto HyperClockCache variant that's coming should make sure that there's no like usability problem for getting that that feature. You don't have to provide this hint. And hopefully this could be towards a unified sort of generally good configuration, at least for like large database use cases. More configurability maybe. Hyper LRU cache, I don't know. It sounds like a tough problem. Hopefully we're going to get some. I'm expecting to work on some filtering, sort of automatic bloom filter work soon. Hopefully that HyperClockCache will help with that.
Wow. Okay. Perfect. Thank you so much, Peter. Very interesting. Let's see what questions do we have. From Niv, thank you for the great work and talk. Have you considered caching data at the level of entries rather than blocks? This could prevent memory wastage while also preventing the problem of compaction evicting useful blocks.
Yeah, so RocksDB does have a feature called row cache, which will cache entries. It adds some level, it adds an extra layer of sort of lookup. I think in our biggest use cases at Meta, where we have large DBs and the density of how frequently is this key accessed, that density is quite low, and we for a lot of our data we're using really heavy compression. I think those factors, we tend to put more engineering effort into those sorts of use cases. And I don't think row cache offers a great value for those sorts of use cases. Prevent memory wastage. I guess that's a fair point that, if you're caching a whole block for a single hot entry, that could be, wasting space.
Mm-hmm.
It's a tricky problem. Good point. And we might explore. We do have some people interested in row cache in Meta, and we might there might be some motivation to try and get it working with HyperClockCache. We will see.
Okay, thank you. I see that we don't have any other questions, and we are also over time. So, Peter, thank you so much. That was fascinating. I know you have more of a drill down session. Maybe we'll have that at some point. Very interesting. Looks like an amazing work. I know we use it internally in some scenarios as well. Thank you so much. Thank you for joining. Thank you for having this talk, and thank you for writing the HyperClockCache.
Thanks for having me.
Sorry?
I asked if you want to add anything.
No, just thank you for Peter for everything. It was super interesting. And I want to invite everybody to join the Discord.
Well, Peter is also available for questions, by the way, if you want to ask any questions on our Discord.
Absolutely. And join us, ask questions. And this session is recorded. It's available on YouTube, Twitter, LinkedIn, Facebook. And if you have other ideas, other interesting topics that you want us to do a session on, please share with us. We'd love to provide more relevant content. And that's it. Thank you and have a great weekend.
Thank you.
Bye, guys.